This biochar activation is something which will add lots of value to the biochar that is produced, as you understand even from your own experiments and studies that you have done. So in this process, how the usefulness of biochar will increase, its own characteristics will enhance and improve with increased the porous structure, that is ultimately the surface area of the biochar, which will help in right from absorbing pollutants to nutrients absorption and many other values that it would create. So, what are the various activation methods, and can you tell some of the simplest to again industrial scale activation processes like?
Yeah, sure, Dr. Sai, and thank you so much for giving this opportunity once again. And really, it is very interesting topic and very close to my heart on the activation of biochar. So, biochar, as we all know, is produced when biomass is pyrolyzed. And in last video also we talk about pyrolysis, that it is heating of the biomass at a high temperature. That temperature can range from say like 400, 500, 600 and so on. So pyrolysis is heating to a high temperature in absence of oxygen. So we call it as limited supply of oxygen, but here I will call it in absence of oxygen or in presence of an inert environment, so that the combustion will not take place and the biomass body that is made up of organics, say cellulose, hemicellulose, and lignin, they start breaking down and volatiles will leave the surface and carbon will left behind. That is majorly known as biochar. Now, this biochar has limited application if we talk in terms of surface area and pore volume, if we are making it at lower temperatures. So, different factors that affect the biochar properties includes the temperature. Temperature is the first and foremost important factor that determines the characteristics of biochar. So, a biochar that is prepared at say 400 degrees centigrade or 350 degrees centigrade will also appear like a black material only, and a biochar that is prepared at 700 or 800 degrees centigrade will also be appear in the same way, a black material, solid material. So you cannot differentiate on just looking at it, but temperature plays a vital role in changing the chemistry and in changing the surface area and the different properties of the product. So, at higher temperatures, all the volatile matter that is there in the plant body, it because of high heat, it starts escaping out from the body within the reactor. And in doing so, when the volatiles get released, then their pores are formed at their place. So, it depends.
Can we say something like in proximate analysis, there is a sequence of events, for example, right from the moisture. Let us say moisture itself is an embedded thing within the any biomass. First, that gets expelled. Then again, these volatiles, they also will get expelled. So in the process, something like purification kind of situation will come.
Right.
Then afterwards, we have other impurities or like ash and other things also will be, I think, in the process eliminated. Then finally, what is remaining is biochar, something like that.
Right.
So can we go
So,
in that sequence in understanding this whole how this
yeah, sure.
porosity develops?
So let me start from when we are putting the biomass in the reactor. Then we are increasing the temperature. So heating rate is also very important. At what temperature we are heating, what is the temperature of the reactor. So first of all, the temperature is at room temperature, and when it starts heating, say above 100 degrees centigrade, the plant body is made up of moisture. So first of all, moisture escapes from the plant body at say 100, 105, 110 degrees centigrade, and when the entire moisture escapes and the temperature is going and above and it is increasing, slowly the other fragments of the plant body also starts leaving the surface. So first of all, the material that leaves the surface is a hemicellulose, whose degradation starts somewhere at 250 in between to 280 degrees centigrade, and it starts leaving the surface after moisture leaves. Then after that, cellulose leaves somewhere up to 350 or 400 degrees centigrade, and in the overlapping range again, the third material that makes the plant body is a lignin. So lignin decomposes at a higher temperature. So from 300, 350 degrees centigrade, fractions of lignin also starts decomposing, and its decomposition keep on going till say 500, 550 degrees centigrade. So when char is produced at say 300 degrees centigrade, 350 degrees centigrade, then mainly it is the hemicellulose and a portion of cellulose that is removed. Lignin is still there in the product. Whereas if we are making a biochar at say 700 or 600 or 800 degrees centigrade, then majorly all the three of the materials has been removed from the plant body, starting from moisture, starting from say hemicellulose, cellulose, and lignin. So here the properties of both the biochar will be very different. The biochar that is prepared at 300, the biochar that is prepared at say 600, 700 degree centigrade. As you rightly mentioned in the starting, it is the surface area and the pore volume that are very important factors for determining the use of a particular biochar for its application rather. So how to activate this biochar that we have in hand, be it prepared at 300 or be it prepared at 800. So activation methods, as you said, so there are we can differentiate it into three ways, like thermal activation and physical activation and chemical activation.
The harder biomass like coconut shell
Okay,
biochar, what we say, that is said to be having high
lignin.
porosity. Yeah, it is having high lignin, so high porosity, let us say. So between the cellulose material and lignin material also, I think if you have more cellulose material, it may not have so much surface area, something like that. If it is
Yeah,
having high lignin, then it is going to have higher the porosity or surface area, let us say. Second thing is the density of the biomass. So how do we see these factors also in contributing to the ultimately the activated part of the biochar? Yeah, this is fundamental, no? Because when we choose a biomass, that itself defines its nature. The
yeah, yeah.
characteristics of biochar are based on the feedstock. Yeah.
Right, very right. So if our plant body is having more of cellulose and hemicellulose, then definitely when we pyrolyze, then three products are formed. The gaseous products are formed, liquid is formed, that is called as bio oil, and biochar is formed, that is the solid component. So if the plant body is rich in hemicellulose, means it's soft, tender plant body is there, more greeny is there. So you will get more gases, and biochar amount will be less, because biochar is mainly from the more the lignin content, the more the biochar will be there. More the cellulose, more the hemicellulose will be there, more the gaseous products will be there. So as you said, lignin is the key component for the biochar. The harder the material, the better the biochar will be.
Perfect, because this is what many people don't understand. Why different types of feedstock generate different types of biochar, but when we see the value, whether it is for combustion value or whether it is for application value, right from soil amendment to environmental applications or anything like that, so it is a highly variable thing. So
Right,
fundamental thing is here because ultimately activated is a one step forward from
right,
what is produced as biochar, the basic biochar. So again, the basic biochar itself has some characteristics based on the feedstock.
right.
So this line of understanding is very, very important in the activation process.
So basic characteristics for all the type of biochar, they it falls into two categories: the proximate analysis and the ultimate analysis. Proximate analysis is consisting of, in a plant body, what we do is we first keep it in oven and we remove the
Mm.
moisture, right? So after the moisture has gone, we keep it in furnace to remove the volatile matters.
Yeah,
So whatever the volatile matter in the plant body is there, they will escape in the furnace. And whatever will be left behind, then we do the ashing of the material in the
exactly.
furnace itself.
Mm.
So what will be left behind is the ash only. And what is ash? Ash is just the mineral matter. Mineral means all the inorganic components. What are the inorganic components? Just like we have sodium, potassium, magnesium, calcium. Then we have iron. We have silica. So all these together forms the ash. This is a very common phenomena that we have seen a number of times whenever we do combustion. Then at the end of the combustion, what is obtained is nothing but ash. So that is the inorganic components that are present in the plant body. We call it as micronutrients also. So it comes in the form of ash. Now, after removing of moisture, volatile matter, and ash, if we add them, then it does not add to 100. So when subtracting from 100 all the three quantities, we got the fixed carbon. Fixed carbon is that amount of carbon that is not even degraded at, say, ashing temperature. So that is the amount of carbon, fixed carbon, that is present inside the biomass.
Yeah, good. So ultimately, in proximate analysis, there are four things that are tested finally.
Yeah.
So moisture, two, then volatiles,
Then
then
ash.
ash, then fixed carbon. Okay.
And then comes the ultimate analysis. Ultimate is the chemical composition basically, like what percentage of carbon is there, what percentage of hydrogen is there, what percentage of nitrogen is there, what percentage of sulfur is there, and what percentage of finally oxygen is there. And oxygen is also obtained by subtracting from 100 from all these percentages of carbon, hydrogen, nitrogen. It is by difference we obtain the percentage of oxygen. So these proximate analysis and ultimate analysis, these two are the basic tests that is done for each and every carbon. Biochar here we are calling it as. So for every biochar, we do all these two tests, proximate analysis as well as ultimate analysis, to characterize it, to know like what was the moisture, what is the volatile in the compound. If the biochar is prepared at a higher temperature, say 800 degrees centigrade, then the amount of volatiles will be very less and the amount of fixed carbon will be high. Whereas if the same carbon is prepared at say 400 degrees centigrade, 450, then the amount of the uh, volatile will be very high, and this will be less, fixed carbon will be less.
So this aspect, I think many are confused. So you can bring the difference between these two analyses and why they are required.
The proximate and the ultimate analysis, right?
Yeah, both. Why the carbon difference is different. There it is fixed carbon, we know, but here it is carbon. Yeah.
Okay. So, in case of CHN analysis, or you can say the ultimate analysis, so here the carbon that is tested is the total carbon present in the body of the plant. So, the protocol says that the body is combusted in the elemental analyzer, the plant body. You can say the biochar is combusted in the elemental analyzer, where carbon is converted into CO2 completely. So, it is the total carbon present in the plant body. Whereas when we are doing the proximate analysis, then a portion of carbon is being removed as volatiles, because
Yes.
volatile matters are made up of organics only. Organic compounds are only volatile in nature, like they will they will get evaporated from the surface at higher temperatures. So the carbon is going on in that also. Then you have this ash is a part of the plant biochar that is not removed as volatiles. So it will be there in the uh, plant in the biochar itself at higher temperatures. Now, when we are subtracting it with 100, then what is happening is moisture and the carbon that has been removed and the ash. We are subtracting that and we are seeing that certain amount of fixed carbon is still there that is not being able to be oxidized at a higher temperature. So that is why the fixed carbon is lesser uh, in comparison when we talk of the total carbon. in the CHN analysis is different and the fixed carbon content is different.
So we can continue with this activation process now. Okay. Yeah.
Right. So, if we see the activation of biochar, when we are making biochar, at that time also activation is taking place.
Yeah.
So, it depends on the temperature we are making. If we are making at a lower temperature, then the porosity produced in the biochar will be low. If we are making at a higher temperature, more of the volatiles will be removed, a very cleaner surface will be formed. So, the porosity will be better than the biochar that is prepared at a lesser temperature.
Yeah.
The pores will be more clean because at high temperatures the organics will break down and they will leave the surface. So this is known as thermal activation, where we are not using any external agent to activate the surface,
Yeah.
right? So thermal activation done at 800 degrees centigrade, 850 degrees centigrade, or at 600 degrees centigrade will yield biochar with different surface area and different pore volume. So we can say that on a surface of biochar, we have three type of different pores. We have micropores, we have mesopores, and macropores. Now in micropores also we have ultra micropores. So they are lesser than you can say 2 nanometers. The pores that are between 2 to 5 nanometers and more than 2 to 5 and more than 5 nanometers becomes a macropores. So again, micro, meso, and macropores are there on the surface of the activated carbon. Now,
Yeah.
based on the porosity, we decide the application. For example, if we talk for the gas cleaning or if we
Mm.
talk for the gas adsorption, then gas molecules are very small molecules. So, very small, ultra pores are required for their adsorption, means anything lesser than zero point 0.7 nanometer or 1 nanometer, lesser than 1 nanometer size pores are good to absorb gas. Whereas if we talk for water purification application, then water pollutants are bigger in size. You can say 1.5 nanometer, 1.7 nanometer. So with such a bigger pollutant, how it can enter into a ultra micropore? So the surface of the carbon should be tailored or should be designed in such a way that uh, it is good for the pollutant we are looking for the removal. If we are looking for a gas pollutant removal, then the ultra microporous surface should be prepared with proper functionalities so that that pollutant can be absorbed and not only absorbed, it should not uh, move out of the pore. It should be held there for a longer time. Equilibrium should be established properly. Whereas if we are talking for a water pollutant, then if the pore size is so small, then whatever equilibrium time you will provide, it will never be able to absorb on the surface because of the small pore. Therefore, this is my personal experience when I was doing PhD. Then I came across a student that my carbons are not giving proper iodine values. Whereas I was saying that my carbons were very high iodine number. So then we found out that the carbon she was preparing was macroporous. The pore size was 50 nanometers, was say 100 nanometers or something. They were very wider pores in which the iodine molecule, such a small molecule, was just going inside and going back again. There was no absorption taking place. One is the thermal activation where temperature only plays and there is no external agent taken into consideration to activate the biochar. Only we see that what is the effect of temperature on the properties of the developed biochar in terms of BET surface area, that is called as in meter square per gram surface that is developed because of the effect of temperature, increase in temperature, the removal of volatiles. Now, second comes when the external agents are playing their role. So there are two type of activations. One is the physical activation and another is a chemical activation. Then the physical activation, again, we can divide into three parts. The first is the steam activation, that is, we are using steam as an activating agent. Then second is the we are using gas, carbon dioxide gas, as an activating agent. Then third is the combination of the two, where we are combining steam as well as CO2 to use it as an activating agent. So the first category, physical activation, can be studied into three parts as the steam activation, CO2 activation, and a combination of these two activating agents. Now, let us talk about the steam activation. So, again, in
So
steam activation,
temperature activation, that is, let us say I have a biochar produced at 400 degrees, 450 degrees. I have biochar produced at 550 degrees. I have the biochar produced at around 700 degrees, like that. So definitely the biochar which is produced at around 700 degrees will have more porosity or more activation. Yeah.
right,
Then so this is what you said in the temperature
thermal
activation,
activation,
thermal
right,
activation. Okay. So now we are adding two other things.
yeah,
One is that
physical
activation through
activation,
steaming, as well as activation through CO2. Yeah.
yeah, and a combination of these two, all the three comes under physical activation.
Means if I add something like quicklime or something, does it also add value to activation process?
Quicklime.
Yeah.
See, quicklime is again, it is a chemical, so it should not come in physical activation. CO2 that is liberated after reaction with steam, because quicklime is solid and it will react chemically with the volatiles that are trapped inside the biochar. So if you are passing steam, then is what steam is doing? Steam is reacting with carbon with a Woodward's reaction, where C plus H2O is reacting to form CO and H2. So it is the carbon that is reacting with the steam at a higher temperature and it is getting converted into CO, CO2, right? And hydrogen or H2O is formed again. So steam is one thing that is available in most of the industrial processes and all over our country. Steam activated carbons are the most common activated carbons available in the market because of the availability of steam in the processes and no additional cost because steam, if it is available in your process, then you can easily use it. So while doing steam activation also, you need to understand different parameters like at what temperature you have to activate it. What is the quantity of steam that you have to use for the activation? For how much time you have to activate it? What should be the packing density of the material inside the reactor while doing the steam activation? What should be the pressure of steam for activation? How much moisture content should be there in the steam? If it is super saturated, it is saturated, it is wet steam. So steam temperature also plays a role. So
Quality of water also matters. That is
yeah,
used in the
quality
steam
of water,
activation.
true. Quality of
Pressure,
water,
at what pressure we are pumping the steam,
right,
the quality. Yeah. And
right.
I think in the pyrolysis units, we have lots of heat energy. So this heat
True.
can be linked to the boilers for generation of steam. And then and there, wherever the pyrolysis is happening, at the end, in a way, it is a kind of quenching also, let us say. Even if there is anything spark left in the biochar, and the steam activation process, it will be completely, means there won't be anything left, any spark or anything within the biochar at the end product. Is it so?
Right.
One way. See, when, let us say it is steamed or biochar.
Mm-hmm. Mm-hmm.
So in the process, if there is any spark left from the pyrolysis unit within the biochar, see their biochar ultimately they are embers, they are cooled. Okay, when they are cooled, even there could be a spark left within the biochar. So when we do the steaming, completely you are quenching it. Yeah, in a way. So it's cooling it completely. Yeah.
You're quenching it or we do not see, there are two ways of doing activation. Either you are doing in process, means you have put biomass in the reactor, and when the temperature has reached to a certain set point, say 600, 700 degrees centigrade, then you start putting steam inside the reactor. This is one way. When during the pyrolysis itself you are activating it. So the product obtained will be very different. Now, when you have made biochar and you have cooled it and you have obtained a biochar and then you are activating it again. So these are two different processes where the volatiles are already trapped, where the volatiles are escaping out and you are treating with the steam together. So the product formed will be different.
So it is more like scrubbing when it is in the process directly. Yeah,
Yeah,
away
you can call it as a scrubbing because steam will definitely react with the volatiles
volatiles.
that are forming and that are having a tendency to deposit again within the reactor. So when you are passing the steam, then that steam will react with those organic compounds as well, and the reactions will be different and the product obtained will be different. Whereas if already the biochar has been formed, already the vapors that were there within the reactor, they have condensed and biochar surface has been formed, and then you are again passing the steam in the separate process, then those volatiles that already formed the surface, now they will be again reheated. At what temperature you are passing the steam? Suppose you have prepared
Yeah.
biochar at 800 degrees centigrade. So the volatiles that were there at 800 and they have cracked again and again and they have deposited at 800 degrees centigrade. And now you are doing steam activation at say 500 degrees centigrade. Then the product obtained will be very different. Whereas if you are doing uh, if you are making biochar at 500 degrees centigrade and then and there you are passing steam. So in both the cases, the product form, the geometry, the surface area, everything will be different.
Which is better, after cooling steaming or directly when at 500 or 600 when just it formed steaming is better, which
It
will add more
depends.
value.
It depends. If a person is having the facility and of pyrolysis and is doing biomass pyrolysis in the facility itself, and the steam is also available, and for what application you are looking for. So, and which biomass is there? Because biomass is so heterogeneous and so different in nature that you cannot uh, standardize a particular process for a particular application. Every biomass will have a different characteristics and will have a different parameters for activation. For example, if you are using, say, cashew nut shells and you are using CO2 for activating, or you are using steam for activating. Whereas if you are having cotton stock and you are using steam for activation or CO2 for activation, then the surface area produced will be very, very different.
That's what I mean to say, which one could be better when usually what we say when we are making dosha or we are making something on a pan, when it is very hot, when you put water, the holes formed will be very fast actually. Yeah. So when it is very hot, actually immediate reaction will happen and then the
Gasification will be more.
porosity will be more. Yeah.
Porosity will not be more, like more gasification will be there. The surface may be deteriorated even because of extreme reaction.
Yeah.
The entire carbon can be gasified.
Yeah. That is also there.
That is also there. So this we need to see if it is economically more suitable, because when you are making biochar, then already the temperature is there. Already it is 500 degrees centigrade. You need not to reheat again. You need not to
So what I was thinking is probably when you want to have this bio oils and something like that, then definitely steaming is not a good idea because you want to use it as a fuel for something else, as a blend for something else. But I think when you are looking like wood vinegar or when you want to apply this for plants and agriculture, maybe this steamed water with volatiles as a scrubber, Okay, the steam acts as a scrubber for the volatiles and catches even what is going out, and that is collected in liquid form. This can go something like part of wood vinegar, which is diluted. So this will have its own value for applications, especially for the soil and agriculture, something like that. So maybe the choice is here between if you want to have this uh, bio oil, something like that, or even pyrogas if you want to have, then the steaming is not recommended probably. So scanning electron microscope images with the scale, something like that. Okay. And another thing, apart from this physical treatment, from temperature and steaming and CO2 like that, we have acid treatment also in activation. So, what are the acids that are commonly used on a commercial scale or even a domestic level? I used to suggest lemon water, yeah, or vinegar. At domestic level, if somebody want to treat their biochar at home. So, what is the other acid treatment methods?
Yeah, so see, as far as chemical activation is concerned, so it has different drawbacks associated with it. First of all, you will treat, no doubt the surface developed is far better than any physical treatment. But at the same time, you need to remove that chemical from the product, final product. So a lot of water is consumed in washing and rewashing, and then that waste water is generated from the process. So treating that wastewater becomes a challenge. The quantity of water required to clean the surface. So if you see, then chemical activation is at industrial scale is not preferred much because of the cost of treatment. It goes high, and the waste is generated. Much waste is generated. If you see for what are the activation agents in chemical activation, then definitely acids are there, bases are there, or you can say salts even are there. As acids, they are harmful to the nature. So many studies you will say on sulfuric acid, on HCl as an activating agent, on different type of acids. Even organic acids are very good to activate, as you mentioned, lemon acid. Even this wood vinegar that is coming out, I activated some few samples with this wood vinegar also, and the results were promising. So
Something like phosphoric acid because it can go well with soils. Sulfuric acid in alkaline soils, it can go well, let us say.
yeah, phosphoric acid, lot of research has been done with phosphoric acid also, but at the end of the day, the amount, if you are producing 1 ton of activated carbon, then the amount of phosphoric acid required will be in good amount, and where you will dispose that. If it is like it is good for soil, but in what quantities? So again, this becomes a problem of pollution, environmental concerns. So like there are some of the chemicals, like if I talk of some salts, then they do not pollute environment. They are food additives also. uh, I'll name the chemical like potassium carbonate is there. But then it gives very good results. But then the removal of potassium carbonate and cost of 1 kg of potassium carbonate doesn't bring viability to the process.
Similarly, potassium hydroxide or sodium
Many,
hydroxide.
many, many, many studies have been done. Extreme researches has been done on these chemicals of KOH, and they are wonderful chemicals. They will give you beautiful surfaces, high surface areas above 2500 meter square per gram. But then uh, they are not uh, economically viable on commercial scale, on industrial scale. Still, we are only having coconut shell activated, steam activated carbons, or at some places now other biomass have started taking place. But steam activation is the most common activation among all.
Yeah, environment friendly and always at the source we can generate that much steam
Right.
with the same biomass or the leftover heat. Yeah, this can be go with the chain of production.
There are
That's good.
certain species in which, if we say for karanja seed cakes, then the inherent potassium oxides are very high. This potassium oxide percentage is high as a mineral. So when we activate thermally also, then the surface of the carbon from Karanja is very good. If we do steam activation with the Karanja seed cakes, then results are promising because the plant body itself is having good percentage of catalytic activity takes place, good percentage of potassium is there that act as a catalytic agent during the process. So
So yeah,
inherent minerals also play a role. If we talk of say calcium carbonate, then calcium carbonate melting point is very high. It is above 1000. So it cannot act as an activating agent at a lower temperatures because it will not react with the carbon. So every chemical has its own challenges, has a chemistry behind, and we should just focus on if we are talking of commercial scale R&D, everything is good for research, but if we are going for industrial level, then economics matters a lot. At the end of the day, we are left with steam activation as one of the most feasible solutions.
yeah. Ultimately, I think the activation of biochar helps its characteristics to improve, so that with less quantity we'll have more benefits. So I think high-end applications like VOC's removal in the aircrafts, let us say air purifier. So really there, because we need less biochar, activated biochar, to treat so many passengers traveling in the aircraft, let us say, or like RO filter. Then we have this activated carbon filter. So we want that to last at least 1 year for a family minimum. So it means again we need a highly activated biochar within that carbon filter. I think we have specific applications of activated biochar, but not at the scale of agriculture as of now, because agriculture means we are talking millions of tons of biochar to be applied for the soil amendment. Second thing is, here actually there are so many contaminants and pollutants existing within the soil, otherwise also. Anyhow, they will be occupied by microbial life. So microbial life, when they occupy, I think what they want they will keep, what they don't want they will remove. So it's a continuous cyclic process that happens within the soil. So I think we need not worry much about this biochar when it is applied for soil amendment. Yes, definitely for environmental applications, I think like wastewater treatment plants are in many chemical industries which are very specific to treat certain chemicals or filter. I think they are required. So this way, I think this activated biochar has its own values and applications well defined, and with now existing technologies, only as you said, environment friendly steaming.
I would like to add one thing, Dr. Sai. As you said, for the soil amendment, we can apply anything. So here, volatile metals should not be high because you see this polyaromatic hydrocarbons or polychlorinated benzenes, PCBs, they should not be there in biochar when we are applying to it to the soil because they will finally contaminate it. So proper pyrolysis should have been taken place while applying it to the soil because otherwise the plant body will absorb it and again you can say contamination or contamination of the soil will take place and again it will come to the human body itself. So
Maybe
carcinogens should not be there, volatiles should not be much in the biochar and the fixed carbon should be high and the hydrogen C by H by C ratio should be proper so that it should stay in soil for a long time.
here I mean to say two, three things actually. First thing is the quantity of biochar that we are applying to soil as an amendment. If we take even 1 hectare of land, about 8 inches thick soil, maybe around 5,000 tons of soil is there by weight. Within 1 hectare, if I am applying 5 tons, 10 tons, 20 tons, maybe biochar, the percentage wise that I have amended is maybe 1 2% at the most. Let us say even higher applications also. So that is one factor. Second factor is contamination of soils or water that is given to plants already, or the air pollution that is there around. I think we have so many challenges already around agriculture. So no soil
Right.
is 100% what we say organic certified, because when we have pollutants everywhere. Okay. So I mean to say, to be perfect is ideal, but when you have a soil which is already so much pesticide residue or complex chemical residue and everything is existing, and within this kind of environment, again we are adding activated biochar, the purest biochar. So it is more like dilution. So you are keeping a good guy in the environment of so many bad guys, something like that. So there again, the energy that went into this production of biochar or activation process or the cost already, because this is very huge. That's why I said like that. Otherwise, always we need to be ethically what I'm telling. Whatever we are applying, we are responsible for that. But the process of biochar that is going to remain safe for 1,000 years, in the whole process, yes, initially these 2 3 years that contamination can be there as a remediation of these highly contaminated soils or even mining areas and heavy metal areas, many are there. Initially, if we apply biochar and let something grow, which may not be edible for us, but it adds some greenery and other things, they will absorb these toxics and all that
True.
initially, and later on, after a few years, then biochar is going to remain there anyway. It will not continuously have these things forever. Once they are removed, over. So then we can have this edible kind of all kinds of things. So maybe this is another method to reduce the burden of cost on the farmer. So because always I look at the solutions of adaptability of the communities who are already struggling. The farming itself is not so viable as of now, and there is no policy support in biochar. Once we start telling this is bad, that is bad, and this is not good for anything, what you're doing is very, very bad. I think somewhere we need to take an approach where we start improving. Means with the time. That's what my opinion about this aspect. Yeah,
Very true, sir. Somewhere we have to take a step, and somewhere we have to decide like this should be the baseline.
yeah. So like that, we always have options to do
Right.
actually. So those things we can adopt. So, Dr. Sonal, I think you had very good discussion on this activated aspect. So we'll cut short now our discussion today. And it was good, actually, it was more elaborate. It was not as a person who has done complete analysis of everything. We are like the people who are also learning in the process. Our
True.
conversations will add value like any other person's mind. Those who are reading here and there, some might know answers directly. It's fine, they know. But always this is an emerging science. And yeah, this kind of conversations will help everybody. Thank you very much, Dr.
Thank you,
Sonal,
doc.
and
Thank you so
thank you.
much, Dr. Sai. Yeah, bye.
Thank you.